So the complexity of this one is easy to derive because we look at how n's value is reducing. You start with n and gradually you reduce the value of n all the way until your base case is 0. So you're essentially counting the numbers of times it takes you to go from n to 0, right? So that's essentially n plus 1, right? That's the reason why complexity is O(n). Okay, so I think the first part is okay. What is not okay, I think, is the second part, right? So now we have this power 2 implementation. The original idea is that we want to slice the value of n into 2 pieces, right? By dividing n by 2. And then suppose n is even, then the power of x to the power of n is simply x to the power of n over 2 multiplied by 2 times. Right? If you're odd number, then all you need to do is then multiply this 2, but make up the missing pieces by providing another x in front. Okay, so the tracing of the complexity here is less straightforward, right? Because the numbers of times of reduction is not by 1 every time, right? Now it's actually divided by the size of, by a factor of 2 every time. So you indeed follow the trajectory of log 2n, right? You start with n, then the value of n is reduced to n divided by 2, n divided by 2 squared, until, again, the same base case, which is n equals 0. But the reason why it's more complicated than this is because for each and every level, for each and every call, right, you actually generate 2 additional recursive calls. This need to be taken into account. Not just the step it takes you to reach the base case, but also like the numbers of actual instances that we generate per level, right? Not very straightforward. So like in the statement over here, you can see that one way to trace it is that for definite numerical cases, we put down the number. Here we start with 16, for example. 16, a single 16 would generate 2 8, right? And then for each and every 8 instance, you generate 2 4s, right? And then for every 4 instance, you generate 2 2s. So 1 become 2, 2 become 4, 4 become 8, right? So we need a table to trace it, right? For each and every level, right? This numbers of instances refer to how many instances are we generating for that particular n value, right? You have, if you count, you have a single instance of 16. This is where you begin, right? But when you reach n equals 8, because you are branching out, you are making 2 calls, you have 2 instances. And for each and every 8 instance, you generate 2 4 instances, right? So that's why when you reach 4, you have 4. And then this multiplication just keep going on. And the last instance is actually when n equals 0, right? By that time, these instances already got multiplied by 5 times. 1 to 2, 2 to 4, 4 to 8, 8 to 16, 16 to 32. And you have to sum up all this. Sometimes it's 2, sometimes it's 1, right? But the key thing that's driving it will be the numbers of instances. All right, so here we have a very brief explanation about how the complexity works. Okay, so suppose you have difficulty, like try to like figure out why the complexity is O(n), right? So may I probably provide another potential perspective, right? Let's copy this instance down, right? And try to find regularity. If you can recognize the regularity, then you can calculate the complexity, right? So let's see how we can do this, right? Just probably copy this instance. This is numbers of instances, right? So we want to find what kind of series this one is. All right, so just put it down over here. So effectively, we are looking at these numbers of instances. And for each and every instances, in the worst case, we will generate like 2 multiplications, right? But in the best case, it will be 1. But this 2 is a constant. So it doesn't matter. It can be 1, it can be 2. But in the end, when you come up with the real complexity, it shouldn't matter at all. All right. So what's important here is actually the summation of this number, right? So you have one instance plus two instance plus 2 to a power of 2 all the way until like 32, right? 32, which is 2 to a power of 5. This is basically what we call the geometric series, right? So if you do a Google search, the geometric series in a way is actually similar to arithmetic series. But for arithmetic series, if you think about that, it basically means that from one turn to the next turn, you have fixed differences. But for geometric series, from one turn to the next turn, you have the same factor. It means that the next turn has to be multiplied by the same number over and over again. In this case, the number that's being multiplied is actually 2. Right? So if you want to generalize this, right, if this is your n value, what we are going to do is that you see that the numbers of times that you're going to reach 1, we usually call this is you have this n divided by 2 to a power of k, right? K represent the numbers of times of division by 2 that you reach 1, and plus 1 more, then k plus 1 will be the total numbers of times that you go from n value all the way down to 0 value. All right, which means that if you want to write it out, the generalization basically says that it's going to be 1 plus 2 plus 2 to a power of 2. And the last term should be 2 to a power of k plus 1, right? This is actually how you derive F32. Okay, if you want double confirmation, right? Over here, your n equals 16. So if you calculate log 2n, which is a log 216, this is actually 4, right? And then the last term, k plus 1, is indeed 2 to a power of 5, which is 32. Okay, so this generalization, right? So this help you, by looking at this, it help you generalize how do you write the sequence. And we say that this is called the sum of geometric series. For the sum of the geometric series, right? This is again the second series that you're going to see from this point on very often, right? So make sure that you are familiar with the way that you can apply the formula. So the sum of arithmetic series looks something like this, right? First, we try to write the general form of arithmetic series, which is starting from some initial number. We call it the very first term, A1. And we say that the definition of the geometric series is that you multiply term by a fixed factor. This term, we call it R. So the second term is going to be A1 times R. The third term is that you multiply by another R. It's going to be A1 R squared, right? You continue doing so until you reach the final term, right? Which will be, in this case, you just call it n over here, right? So the very first one actually is A1. You start with R to the power of 0. This is just 1, right? So you start from 0, 1, 2, all the way until n. If this is your formula, this is your series, then the sum of geometric series formula is 1 minus R, right? Or if you wish, we can write it the other way. It's going to be R minus 1, and then A1, R to the powers of total terms. Here, the last term is n, but we start from 0, right? So the total numbers of terms will be n plus 1, minus 1, right? If you want to confirm that this term is correct, you can try it on this term over this particular series over here. You have from 1 to 32. You can use a Excel spreadsheet to sum up everything, and then you can calculate your sum by using this formula. It should be exactly the same, right? So the key thing that you have to do is that this is the general formula, right? Inside this formula, you have 3 numbers. You have to decide what is A1, your very first term. What is your R? What is the fixed factor that you need to multiply every time, right? And finally, what is the numbers of terms that you have? Once you have these 3 important parameters, then you can use this formula to calculate the sum of the geometric series. So if you look at the series that we have up front for power 2, we can see that A1 is actually 1. the very first number. The R that we have is 2, right? From term to term, we are multiplying by a fixed factor 2. Finally, the numbers of terms, the last term, which is n, right, is actually k plus 1, right? This we also start from 0, right? 0, 1, 2, all the way until k plus 1. All right, so this is the n value. So with these 3 values, we can then insert that into the formula, right? So we have 2 minus 1. A1 is actually just 1. And then we have 2 to a power of n plus 1. N equals k plus 1, right? So you have a k plus 2 over here. And then minus 1. So if you do the calculation, it's going to be 2 squared times 2 to a power of k, because you have this k plus 2 over here, right? Minus 1, right? So again, the key is that what is this 2 to a power of k, right? So k, as we noted up here, right? K referred to the numbers of times it take you to go from n down to 1. This is what k means, right? So in other words, if we start with our input variable is n, then k is actually log 2n. This is what k means, right? So if you insert this back into this formula, right? So we can have a final formula over here. We will have 4 times 2 to a power of log 2n, and then minus 1. But this, if you look at it, is just n. Okay, 2 to a power of k is actually n. Again, if you want a confirmation, look up, right? Here at this point, this is 216, for example. This is 2 to a power of k. Symmetric, right? You go down from n to 1, right? And then the numbers of instance increase from 1 to n. Okay? So the final count that we have as a result will be 4n minus 1. If you take a big O, that's the reason why you have a linear time, right? You drop the coefficient, you drop the lesser term. So you have On as the final complexity. Right, so this is a more elaborate form of like, instead of trying to explain that by a vague statement, this is the exact steps, right? If you really want to find a step, this is the exact step that will lead you from the table that we have summarized to the final complexity statement, right? So this is the power 2. So if you look at this design, the original idea is that this supposedly should actually save us time, right? Because we are dividing the value of n by 2 every time. So the reduction step supposedly should be log n. And the reason why this is actually not bringing in the benefit, I mean, in the end, although we do more work, the algorithm look more complicated, but the end result in terms of complexity are still exactly the same as power 1, which you are reducing the value of n by 1 every time. Right, and the reason why that is the case is because we have all duplication, right? If you look at this recursive tree over here, you see for each and every number, the lower the level, the more numbers of times that we are duplication. We have duplication in the instances. We have a lot of 8, 4, 2, 1, and 0. And the reason why we have duplication is over here, right? When we split it into 2 parts. When we calculate the value, for the first value, we invoke the recursive function. By this time, actually, we already know what is the power of x to a power of n over 2. But for the second copy, we do it again. And this is completely unnecessary, right? So that's where the potential duplication is. And when you think about like how to improve the algorithm, duplication is always that's places where you can begin with, right? We look at this process, we recognize that there's a duplication in the second call to the power 2 function. Not necessary, right? You are making exactly the same call. So if you look at like what we have in the tutorial question, right? So the part that's being taken care of is power in the power 3 function. Is that this function, after we calculated the value of it, we store this value as a local variable. So for the second time, when we are about to return the multiplication of these two values, we do not need to make duplicative call. We make the call one time, then that's enough. In terms of the numbers of instances, instead of this growth that we see over here, you have a single instance for each and every level of the n value, right? So that's how we can actually just enjoy this reduction in log 2n, but we do not incur additional instances like what we have over here, have a lot of instances.